Ah, happy Monday. Welcome back. Today we're going to be getting into the most important law of all science. Honestly, Newton's laws only scratch the surface of science. The law of conservation of energy is the one law that you have studied in all your science courses without ever knowing what it is. So there's a lot of words here that I want to kind of get into and kind of explain what this means. As always, the Newton's cradle is a great example of what we're talking about here. We have the two weights lifted up on either side, and they each have energy. We know they have energy because now they have height and motion. They have PE and KE. So when they collide, what happens to their energy? It is conserved. So here is what the law of conservation of energy says. Energy cannot be created nor destroyed, only transferred between types of energy. Energy just never appears. Energy just never disappears. It's only transferred to other types of energy. Now, this is going to get a little confusing, so let's break this down a bit. When I see the word law of conserve means like to save. Try to conserve resources, or you're a conservationist, you're trying to save things. So it's the law of saving energy, of understanding that energy just doesn't disappear, it doesn't appear, it is conserved. That's what conserved means in the scientific sense. Only transferred, not created, not destroyed. So there are several types of energy that exist in the world. I just put 6 up right here. These are not the only 6 types of energy that exist. Last week we went over these two, potential energy and kinetic energy. So potential energy was dependent on the height of an object or its potential to fall. But if you had more height, it had more potential energy. Kinetic energy was related to its motion or velocity. Okay? We had those equations last week. We will get back to those, don't worry. But not today. Today I just want to build a concept of what these things are really trying to say. Thermal energy is the energy of heat. If I think of the word like thermometer or thermostat or thermos, this is talking about heat. Heat is another form of energy. Okay? Chemical energy is a form of energy that you probably don't necessarily realize how important it is. Because if you eat food, the energy in the food is stored into chemical energy. Your body digests it and turns it into other forms of energy that allows you to move. So when you eat food, you are turning the chemical energy in food. So sugar, I'm going to put sugar right here. You are putting the chemical energy of food into your body to allow you to move, allow your body to have kinetic energy. That's an example of conservation of energy. You're taking the energy of food and allowing yourself to move with it. Nuclear energy, you may have done in chemistry. I don't want to get into that now. It's very complicated, but it has to do with the energy in atoms. And I'm sure, again, you probably don't know too much about this, but electrical energy is absolutely energy. It has to do with electrons, another form of atoms. But it's all energy. It's all conserved. It doesn't appear, it doesn't disappear, it goes somewhere. So like for example, if you have a light on, it's been on for a while, it's converting some of its electrical energy into heat energy. You know this because if you touch it, it's hot. It's an example of conservation of energy. Light is energy. I didn't write that down, but there you go. Sound is energy, vibration, all these different types of energy. So energy just doesn't appear or disappear. It always comes from somewhere. So in the whole universe, there's only a certain amount of energy, and it's just getting shuffled between the different types. Little odd to think about. Okay, so let's only talk. I know I just mentioned all those other types of energy. I just want you to know that's the thing. Let's only talk about these two types of energy, potential energy and kinetic energy. For the purposes of our class, let's just assume those are the only two energies that exist. You know there's more, but let's just assume it's potential and kinetic energy. So the total energy is always equal to the sum of potential and kinetic energies. So let's just say that this boulder is sitting at the top of the cliff right here. All right? Let's just say it starts off with 50 joules of potential energy and 0 joules of kinetic energy. And the total energy never changes. Now, if I remember correctly, I just add these up, and it equals this. So the total energy never changes. Okay. But let's just say the boulder then falls. It just falls off the cliff. It was sitting at the edge and it just fell. As it falls, it gets closer to the ground. Here, it's closer to the ground than it was up top. So it has less potential energy. What is its kinetic energy now? Well, the kinetic energy was 0 up here because it was not moving. It was at rest. It was at rest up here. We knew that because it said 0 kinetic energy. But now it's not at rest. Now it's falling. It's speeding up. But I know that at every single spot, when I add the PE and the KE, for this situation, it always has to equal the same total energy. The total energy is never going to change. So in this case, the total energy has got to be 50, which means the potential is 35, and the KE has got to be 15, because 35 plus 15 is 50. Okay, what if you're right here? As the boulder continues to fall, it's going to be even lower. It's going to be even lower. So that means the PE's got to be less than 35, because it's got less height now. The height is going down. Again, at every spot, it always has to add up to the same total energy. The total energy never changes. So 38 plus what is 50? Bam. Then it hits the ground. Now I know it hits the ground and then it's going to transfer its energy to the ground and then it's going to stop moving. But let's just say this is the moment it's hitting the ground. The second it hits the ground. Now it has no height, so all the energy must be kinetic. At every spot, when you add up all the energies, it always added up to the same number. So the total energy never changed, but all that happened was that the types of energy changed. As the boulder fell, let's just look at the PEs. As the boulder fell, the PE went down. As the boulder fell, the KE went up, because the energy was transferring from the potential to the kinetic. So here we go. Here's another situation. Here's a ball rolling down a hill. What this is the same ball at 4 different points in time. Okay, so we could just call this 1, 2, 3, 4. All right. So again, here you have the most PE. Here you have the most PE because of the 4 seconds, of the 4 different points in time, it's the highest. It is just objectively the highest. That's how you know it's got the most height. Now, when is the ball going to be going the fastest? Just logic. The ball is going to be going the fastest at the bottom. Most KE. Kinetic energy. That makes sense because as it rolls down the hill, it's going to be speeding up and speeding up. As it speeds up, it's going to have more velocity. So again, the energy is transferring. So it's as the ball rolls, it loses PE, but you can't lose energy forever. It can only go to a different type of energy. And what happens is it gains KE. Okay, that's it. So here's a very tricky question. I have 4 spots on a roller coaster. Okay, A, B, C, D. You can see them right there. I want to know most. Which spot has the most PE? You know what? Let's rank them. Let's rank it straight up. 4 spots. I want to know which one has the most PE, which one has the most height, which one has the most KE, and which one has the most velocity. We're going to rank them from most to least. Okay? That's all we're doing. That is all we are doing. Going from most to least. Okay, so I know that potential energy depends on height. So the order for these two are actually going to be the same. Whenever you have more potential energy, you have more height. Whenever you have more height, you have more potential energy. So of the 4 letters, which one is the highest? A is the highest. So A has the largest height and the largest potential energy. Then, after A, what is the next highest one? D. D is the next highest one. That's what that little dotted line is. The dotted line is trying to say to show you that the D is a little bit higher than the B. The B would be the next. And then the lowest one, the one with the very lowest height, would be C. All right? Okay, so that's easy. You just look, you kind of boom, 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 rank them up. Now, how does it work with velocity? Well, when the PE is the highest, the KE is the lowest. When the PE is the highest, the KE is the lowest. In fact, they're actually opposites, because as the PE has the most energy, that means when the PE has the most energy, that's when the KE has the least energy. So we know that this order is actually going to just be reversed for the KE and the V. What do you mean by that? Let me show you. So the KE, if I think about this roller coaster, which letter is it going to be going the fastest? It's going to be going the fastest at the bottom of the hill. That's where it's going to have the most velocity and the most kinetic energy. Oh, so we start here with C's, and that's where the PE and H ended. Which of the other spots then, so it's not going to be this, which of the other spots is going to be the next fastest? This one. If you've ever ridden a roller coaster, think about it. You're going the fastest you're going is the very bottom of the hill. It feels like you're going faster other places. You're going the very fastest at the bottom of the hill. And then at the top, that is where you will have the lowest speed. When you go over the top of a hill, that's when you're going the slowest in a roller coaster. So potential energy and kinetic energy are opposite. In fact, you could even say they're inversely proportional. As one goes up, the other goes down. So today's going to work different. This is the end of part 1. Part 2 is going to be the very next video.